not a cold atom person, so I feel a little bit out of place here, but I hope that I will talk to you about sensors, atomic sensors, quantum sensors, and I think it's a lot of the stuff will be relevant to even the cold atom experiments. And I do know we have a few people who do work with the hot atoms here. Hi, guys. Good to see you. And maybe somebody get converted, because there is a lot of fun stuff you can do with the hot atoms. Also, because I'm giving the kind of a seminar, like more official seminar in the afternoon, that's when I'm going to all show flashy data about the lab. So the morning lecture will be maximally boring. Just warning you. OK, so let's talk about sensors. What can we sensor? Like, if we say about sensor, what can we measure with a sensor? Anyone? Huh? Gravity, maybe. There you have to be pretty careful to measure gravity. Let's make a list. What else? Maybe something a little easier. Temperature, very good. Have I heard magnetic field? Uh-huh. What else? Huh? Maybe torque, yes. Let me add electric field as well here. So electric field and electromagnetic field. So torque. What else? Maybe pressure. I'm not sure the atomic sensor will be very good for that, but like say torque rotation, some motion, and so let me adjust like motion. OK, so we can measure a lot of things. Now, for the atomic sensors, most of the stuff we're actually going to measure is going to be frequency. And that can be the end point of your measurements, like if you're trying to build atomic clocks. Or we have to figure out how we take all this, translate it into frequency, and do it. OK? So that's why the general principle of the atomic sensor is going to work like this. So this, all things, I'm going to call them parameters of interest. Because basically, you're going to design your experiment to measure one of those things or multiple of those things. So parameter of interest, that's what we're going to measure. OK? So this is what we want to know. Then our atoms, so atomic system, is going to be somehow reacting on the changes in our parameters of interest. Right? So in most of the cases, we'll try to figure out how some atomic frequency is going to change so that we can measure this change in the optical. And then, of course, we have the optical probe. Because it's pretty hard to see what exactly happens with the atoms. Not impossible, but usually we like to shine some light, and we know how to measure light. So, and after that, we basically take the output of this light, and we say it in some sort of a photodetector. My favorite abbreviation for the photodetector is this. And then usually what you're going to get at the output, that's what's going to go to your computer. That's going to be voltage. OK. So we need to somehow connect changes in this to the ultimate voltage you're going to record. OK? So how we can do that? So we'll talk about that. But let's imagine that we build this sensor. And I have a little exercise for you guys. Suppose that somebody tells you, your boss or your advisor, that, OK, let's figure one. Let's talk about magnetometry, because that's what I'm going to use as an example for most of the time. And they ask you to go and figure out what kind of magnetometers are there on the market. OK? And if you want to start comparing devices with each other, you need to figure out some metrics you're going to look at, right? So what I want you to do in the next couple minutes, talk to the people around you. It's more fun with the friends. what kind of metrics we need to be careful when we're designing a sensor. Okay? I'll give you a couple minutes and then we'll give you some ideas. What metrics you need to know about a sensor before you start buying or building it? Go. All right, any suggestions? What metrics we need to keep an eye on?
Density.
What do you mean density?
Because if you send a laser and you have a photon detector, for example, you are counting photons. So you have like frequency, you have to adjust the polarization, you have the intensity of the laser also.
So these are the characteristics of the specific system. But if you want to compare different devices, in a sense, you don't care how dense it is or how much light it uses, right? Whoever designed it. So what would be the actual performance metrics we need?
Sensitivity.
Sensitivity, right. That's kind of the first one which comes in time. So this is sensitivity. And this is how much your device reacts on the change in your parameter of interest. And we kind of may think that the higher sensitivity is the better, and usually that works. But what else we should be mindful about? Huh? Dynamical range, yes. Looks like somebody know about this. So dynamic range, basically how fast and in which range you can actually catch these changes. Because you can have super sensitive device, but it can only measure very small magnetic fields, right? Sometimes it's fine, sometimes it's not. What else? Signal to noise ratio, it actually will be contributing to sensitivity. That's what basically determined it, thank you. So we want maximum signal and minimum noise. What else?
It needs to be reproducible. So you have to have so much control that every time you have the sensor working, it's the same system.
Perfect. So let's say it is stability. That's one thing, right? So if you measure things, you want it as stable. Another thing, again, I can add to this or interpret this is accuracy. Believe it or not, on the market, you may find a lot of very sensitive devices which are not necessarily very accurate. So you can detect the changes, but you don't know the absolute value. Anything else?
Operation cost?
Cost, yes. That's pretty important, right? Yes. Okay. Well, let's say that engineers figure it out. Yeah. But it's true. It's very practical, practical things. Anything else? We almost got everything. Yes. Huh? Rate of sampling is kind of go into the dynamic range, bandwidths. You know how fast you can track it. So since I'm looking at the fairly high range, you know. Okay? So one thing sometimes is important is the size. Right? If your excellent device is this big, it may not necessarily be very helpful. And what connected to the side is the spatial resolution. And one thing which often we don't care about, but sometimes we do, is the electromagnetic footprint. So what it means is that if you're trying to measure, let's say, electromagnetic field, and your device start producing and interfering with this field, well, that's not very useful, right? Okay? So we can continue, but I think we hit all the basic one. Great job, guys. So how we stand again, I will be talking, I'm thinking mostly about the atomic-based, sometimes vapor-based sensors. So sensitivity for atomic sensors is varied. There are many, many different devices. I wish I would say it's better than everything else. Usually we're kind of on par with other technology. But sometimes, for example, atomic magnetometers, you can make them as good as squids. Electrometry, you kind of can be as good as some antennas and so on. So sensitivity is a strong fit for atomic sensors, not that great. Dynamic range, usually not that great. Atoms tend to be slow, and we'll talk about why. Stability and accuracy, that's where the atomic system really shine, because if we use atoms as a measurement, the beauty of atoms, they're the same everywhere. They do not degrade. It's not like a late level energy levels deflate at time or get worn out. So that's why for this characteristic, atomic sensors tend to be really, really excellent. Cost, again, that's where the vapor cells usually work quite well, because the glass cell, I mean, it's still expensive, but not as expensive as some other apparatus. Size, it depends, again, what you're doing. So for example, sometimes with the cold atoms, you can get exceptional size and resolution if you're measuring something inside your apparatus. But of course, if you're trying to measure something outside, we still don't have that tiny things. And another thing where a lot of vapor cell-based technology really help is the very low electromagnetic footprints, because many of the sensors can be done purely optically. So that means you have glass and optical fiber. You can build it basically without any magnetic and any metals in principle. So that's another great thing we can have. Okay? All right, so just general idea how we will be talking about sensors. So how, again, the atomic system responds to the changes on our parameter of interest. So for the atomic system, we usually like to pick some sort of a resonance. So I know Raul get an excellent explanation, introduction to the two-level system. So we usually pick up some sort of two levels. And then when our parameters of interest changes or appears, there will be some change in frequency. Let's say if this is frequency of the resonances, we'll introduce some sort of a shift. And then, okay, let me try to be fancy and add some colors. We're basically going to shine a light in here. And somehow, this change in energy levels of atoms will imprint itself in light. How we do it, we're going to discuss a lot in the future. So then for this light, so now change in optical properties. In most of the cases, we're looking for some sort of a resonance. So sometimes it's just transmission or absorption resonance, which we detect. And if the resonance frequency changes or the laser frequency changes, we can find the position of this resonance. For the sensing purposes, we usually prefer a dispersion type resonance. Right? Why? Is because let's say we had our original unperturbed system. Then something changed. If we change it, so this is our laser frequency. Okay? So if something changes, I was here, the resonance is going to shift. So that means that if I had like a zero signal before, now I will have some non-zero signal. And if I know by how much, okay, you guys need to yell if I start writing too small. Okay, it's really hard to judge from the board. So if I know by how much my signal changed, I will know exactly how much shift was introduced. And in a dispersion curve, it's nice because if it shifted other way, my signal will move in the other direction. Okay? But if we have this resonance, we usually know how to convert them in the resonances like this. Okay? So then this is the frequency I want to measure. This is the atomic response to our parameter of interest. This is basically the change in our optical signal. This is what I'm going to record in at the end. Okay. So to maximize the sensitivity, this is, I agree, is probably the most important parameter. We basically can say that the signal I'm going to detect is this slope. It's ds over d omega times the frequency. So this slope will characterize the response. So in this moment, we cannot say that the highest responses necessarily give us a better sensitivity, because we haven't talked about noises yet. You know, if you're increasing in your response, increase your noise, that's really not going to help you. And now, if we start moving and looking at the different optical interrogation system, it's convenient to have some sort of a quick check of how well it works. So for the resonance, if we know the amplitude of the resonance, and we know the width of the resonance, which I will call gamma traditionally, and this is supposed to be A, amplitude, then, of course, without being super accurate, we can say that the response of the system is basically a slope of this curve, and this is proportional to the amplitude divided by the line width. Kind of makes sense. All good? By the way, if you have any questions, just let me know. Okay? So that means that if we have the maximum response, we want highest resonance with the narrowest width. Okay? Which sounds great for sensitivity. Can you see why sometimes having too narrow resonance might be a problem? What other parameters can affect? Huh? Too high response is almost never a problem. Resolution will be fine, because if you have a high response and you shift just by a little amount, you will have a lot of change. You can always damp it, yes. The bandwidth, right? Because you can imagine here, if I have a super response but a super narrow resonance, and suddenly my field changed so much that my resonance is basically here, I have zero signal, which is great. And again, this is kind of the price which you have to pay usually. If you can't find a super narrow resonance, your bandwidth goes down. Yep. All right, but still, we usually want to find the narrow resonance and work with it, because it will give us the strongest one. Typically, the narrowest resonance will give us some sort of a state which has the longest lifetime, right? So my favorite atom is rubidium. That's what I work with. Cesium is fine, too. Other alkalis are OK, but they don't have as friendly lasers as usual. So if we're looking at the kind of good levels for the sensing, let's say rubidium atom. So of course, we have a ground state, 5s1/2. This is, of course, electronic ground state. It's, in principle, can live forever. Then the next state is a 5p1/2. This is the first excited states, or p1/2 or p3/2. Okay, so this is the optical transition. These are great because they're kind of strong. They have strong absorption. They have strong interaction. We'll discuss why having just two-level systems might not be a great idea for sensing. But we usually use this one to do the optical readout. So when we want to see the optical signal, that's the absorption on or some other optical property. On this transition, we're going to monitor. So the other couple states I wanted to mention, that we can have a higher level state. So for example, I think it's 5D manifold. It can be reached with 776 nanometers. And then if you keep climbing higher, think it's 1263 nanometers, you can get to the highly excited states. And P and D, you can choose which one. And you can go through this manifold. You can go directly with the higher level photons, 480 nanometers. And what is special about, say, why I put an N here, is the highly excited state. So we've taken N greater than 20. And these have a special name. They're called Rydberg state. How many of you guys work with Rydberg or studied Rydberg? Very good, yes. So they're all rage in quantum computing and quantum information, and they're wonderful for that. But for sensing purposes, we don't care about the photon blockade. But we do care that in this case, we take electron, we move it very far from the nuclei. You create a giant dipole moment. And therefore, it becomes really, really sensitive to all electromagnetic fields. So that's why we liked Rydbergs. So they have a high polarizability. It's proportional to n in the 7th power, so it's crazy. So the higher you go, you're going to have higher and higher response to electric field. Another fun fact about Rydberg states, they're actually long-lived. Because you remove electrons so far, it's hard to electron to travel back home. So that's why it's actually going to stay there for a while. So the lifetime of the state, if it's unperturbed by anything, it's actually going to be tens of microseconds. Okay? So the resonances can be very low. So this way, we basically found our first favorite state. So working with Rydberg states, they are long-lived, and they're very responsive to electromagnetic interaction, especially electric field and electromagnetic field. Another favorite field, at least for me, it's the ground state, because in reality, we have this hyperfine structure, we have a Zeeman structure. So this is where atomic electron spin live. So we can start manipulating the spin. Because there is no radiative decay, the lifetime is not a problem. So these are another states. And here we have a good, so this is a good candidate for magnetic field, for magnetic detection. Okay. So if you look at our other list of parameters, okay, gravity is a tough one. So you really need to talk to your colleagues who will advise you how gravity can couple to atoms and so on. You have to be really in love with the precision measurement to do that. Temperature, believe it or not, the Rydberg atoms can do temperature. And this is through the blackbody radiation. Remember, I'm not sure where it's covered in Latin America. Usually we talk about blackbody radiation in like introductory physics. If you have anything at certain temperature, it emits radiation. And we just said the Rydberg atoms are sensitive to this. So you can, in principle, try to detect. Not an easy thing, but possible. And for the motion we'll discuss, you can kind of decide what you want to do. You can do all sorts of things. OK, so far so good? Yes?
You said that the lifetime is around tens of microseconds.
Yeah.
Considering still like having warm atoms, like
So this is radiative lifetime. So if I take a Rydberg atoms, put it in a vacuum, nobody's around, that's what it can do. You can always make the lifetime less. Lifestyle is very important for that. But at least theoretically, you can reach this. And I know you guys know that because you were already asked. Like this states, their lifetime is tens of nanoseconds. So it's still much, much longer than that. OK? All good. OK. So I want you to get a very brief reminder about how different things affect the energy levels. I presume that majority of you know this, but it's, I want to make sure that we're all on the same page. So magnetic field. So this is, of course, a Zeeman effect. Do you remember what happens when we have atom and we put it in a magnetic field? they shift, the levels shift. So basically, we introduce, so the Hamiltonian for that is going to be minus magnetic moment times magnetic field, right? And what it does is that we create the energy levels. We create the shifts for the energy levels, which is proportional to some coefficient. OK, I know this gamma is not great. It's different gamma. Let me put B right just next to it. Everything is gamma in physics. I'm sorry. And K. So magnetic field. And then M is going to be here a magnetic quantum number. OK. So for example, if we have an electron, then of course we have spin 1/2. So if we have spin 1/2, then in the magnetic field, if we have magnetic field, then it's going to be plus, gamma B, 1/2 gamma B minus 1/2 gamma B, right? So the level splits, famous Stern-Gerlach experiment and all this stuff. In the more complex atoms, the level is going to shift slightly differently. Again, in my favorite rubidium, 87, you have F equal to 2 and F equal to 1. And in this case, magnetic moments we're going to have is -2, -1, 0, 1, and 2. So without magnetic field, they're all going to be on the same level. And of course, in non-zero magnetic field, they're going to shift by almost the same amount for the two ground states. OK, it's not one here, right? So all of those levels are going to shift by this amount, delta omega B, OK? So that means that if we want to use the ground state levels to somehow measure magnetic field, we will need to track either the change in the magnetic levels within the same hyperfine state and just see at the Zeeman levels, or sometimes it's convenient to look at the relative shift of the different hyperfine levels, which is also possible. OK, so this is this. The next one is electric field. Okay. As I said, for electric field, we really want to work usually with Rydberg atoms. Not that this effect is not working for anything else. It's just all the shifts are much, much stronger the higher the n is. And in this case, it's going to be the Stark effect. And the Hamiltonian is going to be minus dipole moment, times electric field. Right? And here things are more interesting. Again, I'm sure you remember your quantum class, there is a degenerate situation and non-degenerate situation. So depending on which levels you have, you can have a quadratic Stark effect. And in this case, the change in your frequency will be some polarizability alpha times square of your electric field. So you will be sensitive to electric scalar field. And this is actually the case mostly for low L states. So for example, if we're doing like a two-level system, we can get to S or D states. So L is 0 or 1 or 2. And this is where we're going to mostly see the this effect. Okay? If you manage to get your atoms in a more higher angular momentum states, which is possible, there is a lot of fun states there, you can get a linear effect and linear response to electric field. Okay? Now the next one, so this is corresponding to DC electric field. So this is constant electric field. DC Stark effect. There is such thing as the AC Stark effect. And this one is used for detecting the electromagnetic fields. So if it's not static, its explanation requires a little more math, but I think you're prepared with Raoul lectures. So imagine that you have a two-level system. Again, you have ground and electric fields. And now you have some electromagnetic field applied to the states with the Rabi frequency omega, right? You all have done that, so you should know. Hamiltonian, if you remember, for this system is going to be H detuning, and it's all in the rotating wave approximation. Okay. Now, of course, we can do all sorts of things, but the one thing I can do is to look at the eigenstates of this Hamiltonian, right? So that means that how I'm going to see this system kind of from outside. And eigenstates, or eigenenergies in this case, they're equal to lambda plus minus delta, okay, plus or minus delta square plus 4 omega square divided by 2, okay? Now, I'm not going to go through the whole calculations. It's fairly straightforward one. The two important cases we will need to know for the sensing purposes, one, if our electromagnetic field is resonant, so we're exactly on here. In this case, you can see that energy plus minus, it's going to be H lambda plus minus. And this is essentially, let me make sure, it is plus or minus H Rabi frequency. So that means that if we send resonant electromagnetic field, instead of kind of a single level we see, we're going to see the doublet. And this is exactly how they do the measurements in the Rydberg sensors for radio fields. So more specifically, like they have a Rydberg state. So this is, let's say, ND state they're going to use for optical measurements. And then they find another, let's say, n plus 1. Not necessarily 1, any n states. That should be P. So this is the radio frequency field they want to measure. So now, for the optical detection, instead of this system, they're going to see the ND state split into 2. And that's what they're going to measure. We'll talk a little more about that. But the AC Stark shift has a kind of a darker side in it, at least for the sensor point of view. Now, here I explained that this is for the resonance case, we have this nice splitting. Sometimes it's called Outler-Town splitting. But what if we are not really resonant? So the second case, if delta is large, let's say the delta is much larger than the Rabi frequency of your field. And in this case, what is going to happen, again, I'm going to kind of skip the math. I'm happy to tell you more about it if you want to. We're going to have the light shift. Because the states are still mixed with each other, but they're mostly in their original state, what is going to happen is that your state is going to basically shift, but what we usually call the light shift or AC Stark shift. And this is AC Stark shift is equal to Rabi frequency of the field divided by delta. So if the delta is large, then this effect is small. On the other hand, that also means that if you have optical field anywhere in your system, at some point, it will be interacting with your transition. So you are going to have the light shift. Now, why we don't like light shifts? That's actually affect one of our parameters, which is accuracy. So the presence of any interactions in your system are going to produce the shifts on your levels which are not related to your parameters of interest. And the light shift is kind of a really bad one, because if you're using the laser, you do have electromagnetic field in your system. So that's the one we can see. And if you ever decide to dive deep into sensing, you most likely will try to figure out how to minimize shift. And you will see that a lot of people spending a lot of efforts trying to minimize those shifts. Okay? Now, everything I told you about here, that's of course relevant for both cold and hot atoms. But the last one, this is more for the territory for the hot atoms. And this is effect of the motion. It's a Doppler effect. Okay? And of course, what it means, a Doppler effect, that if we have an atom and it's moving with respect to our lab frame, then the resonance frequency is going to change depending on the velocity of your atom. Okay? So this, again, you can have a cold atoms which are moving. And if you want to measure the velocity of your system, you may be able to do that. However, for example, for the thermal gas, where we have, let's say, the room temperature, it's about 300 Kelvin. In this case, again, rubidium atoms, they're kind of on the heavy side, so they're a little slow. It is about 200 meters per second. That's their average speed. And that means that the average shift of the Doppler, for the Doppler profile, will be in the order of 200 megahertz. And that's, of course, a huge number. So that's one of the things we have to deal with the hot atoms, is that the fact that the resonance is going to be shifted quite a bit. Okay? So I think these are basically the main effects. I think I didn't talk about rotations. They will kind of introduce fake angular momentum, but that's a separate thing. Okay? All good? All right. Okay, so the next section, I was thinking we're going to look more on magnetic field measurements. For one, because I think a lot of people are familiar with spins, and you can kind of visualize spin. And also, it creates a really nice model for any coherent superposition in the future. It's just harder to visualize if it's a coherence between the two really different states. But the whole language is gonna work. So let me start from here, maybe. So let's say we have a spin state, and I will use the simplified version of the ground state. So let's say we have something with an angular momentum of 1, just for fun. And in this case, we're going to have 3 different states. 1, m equal to -1, m equal to 0, and m equal to 1. Okay? Now, as we said, when we're going to interact with those spins, at least for the purposes of our sensing discussion, we're going to introduce the optical field. So we go to the excited state. And the easiest excited states we can find at f prime equal to 0. By the way, again, a little trivia. Anybody know where you can find a system like this? In what atomic system you can get exactly this? So the simplest one, actually, you can use the metastable helium. It will give you a very clean system where it's f equal to 1, and then you can choose f equal to 0 on top. But you will need a discharge, which is beautiful. But anyway. Anyway, so this is our simple system. Now, how we can use the light to manipulate the spins. Okay? Well, so first of all, how we can choose which of the transition, which of the spin orientation we work with. Of course, we can choose the light with the right polarization. So because the circularly polarized light carries angular momentum, then if we have this sigma plus polarization for light, it gives the 1 unit of the angular momentum to atoms. So it moves it from m minus 1 to 0. Of course, the sigma minus does the opposite. It adds 1 unit of negative. So it moves from 1 to 0. And then, of course, if we manage to get the polarization of light parallel to our quantization axis, then there is no angular momentum transferred. And this is referred as a pi polarization. So we're going to exploit these properties both to figure out how to interact, how to read out the spin states, but also how to manipulate them, right? Because, for example, if I want to create the actual magnetization in my system, I need to use the optical pumping. Okay? So what happens in this case, I'm going to introduce only one of those fields, right? And in this case, if the atom is in this state and it gets to the excited state, and usually we apply magnetic field, so this transition is just not allowed. In this case, of course, the atoms can decay in both of them. But if you pump for long enough or hard enough, basically you end up with the atomic polarization in the other state. So if we started with m equal to -1, we will find all the atoms in the m equal to 1. So that means, and you will see it often, that m equal to -1 means that the spin is oriented against magnetic field, and spin equal to 1 is oriented along magnetic field. So now we prepared all the atoms in the same orientation. So that thing means that if you have many atoms, you created the actual magnetization in your system. Okay? Okay, great. We did that. How we can now measure magnetic field with that? So there are basically two things we can do. And various types of magnetometers are designed to do that. So let's say we prepared this magnetization, and now we are free to choose our magnetic field. So if, I'll give you the answer for the simple one. So let's say our bias magnetic field is in the same direction as our magnetization. This is spin magnetization. Then, of course, nothing is really going to change. If we can keep the atoms in this state for a very long time, they're just going to sit there. And we never can do that, so in the time, we're going to start losing this magnetization. But this is kind of a little boring system. So what happens if I created magnetization in the direction which is perpendicular to the magnetic field? Is it a trivial question or not? OK, looks like not. So why don't you talk to each other? What is going to happen to magnetization of atoms if you have magnetic field in one direction and your spins are oriented like this? Just check that your neighbors know. Uh-huh. OK, don't get too excited. All right, so it looks like, so anybody, I mean, I know you said already, what's going to happen with the magnetic field? With the spins, sorry.
Magnetic field suppresses the spin alignment.
Sorry, what?
Magnetic field will suppress the spin magnetization.
What do you mean by that?
I think a system like the transverse field dicing model, that when we have a system of spin, if you apply a transverse field, the transverse field makes the spin fluctuate and you suppress the magnetization.
Well, OK, so here, we'll get to that, but I already created magnetization, and now I turn on magnetic field. What's going to happen? It's going to disappear immediately? How? It may try, but OK, so I know several people said it. So it's actually going to process. A lot of, if we start talking about decoherences, that yes, eventually we're going to lose it. But on the very first moment, what is going to happen is, remember, again, introductory physics, we have a torque, which is magnetization times magnetic field, right? So what is going to happen is that at least until anything decohere, this magnetization will start rotating around the magnetic field, okay? So it's true that if you don't have initial magnetization and you apply the longitudinal direction, it will prevent it from creation. But if you already created one, the first thing is going to happen, it starts rotating, all right? So we can think about it in terms of the Bloch sphere, which I think you guys mentioned in the earlier lectures. Basically, if you look at the spin directions, we can say that the poles of the sphere is the kind of our two pure magnetization directions. And then some sort of superpositions of the states, that's what our transverse orientation is going to be. Here it's going to be spin up, plus e to the I some phase spin down, divided by square root of 2, okay? So pretty much any spin states we can describe to be somewhere on the sphere before we start including the decoherences. So the two main types of magnetometers which people are using is one, where you basically apply some sort of an external field which moves you from one pole to another, right? Because now, if you have, where is my resonance systems? Somewhere over there. So basically, these two systems have different energies. So if you provide enough energy to the system, you can flip it from the low energy state, which is minus gamma mb, to the state plus gamma mb, right? So if you do that, you will be able to flip the spin, and that's going to change optical properties. But the kind of the negative for this is that usually this is a low frequency transition unless we're talking some crazy strong magnetic fields. So you need a radio frequency for that, which not always a great idea. More fun is to actually trace the precession of the magnetization. Because you can see that the speed of a precession, we have a precession, something like this. Okay, frequency. And that's going to be, it's known as a Larmor frequency. And this is, of course, going to be gamma times magnetic field. So if we actually measure the changes of this, we will know what is going on. Now, now we have to, of course, acknowledge the presence of decoherence. It would be really nice if we can create the spins and let them precess, and they're going to stay in this forever. In reality, we have to acknowledge that if we have our spins, so first, they're going to have this precession term. So that's the good term. The second one, as I think somebody mentioned, is that magnetization is not going to last forever. If we created it, eventually there are many processes which are going to decoherence. So in this case, now, do you guys use this notation for the unit vectors? OK, good. So what is happening now, if I forget this one for a moment, you can see that basically you start with some spin, and in some characteristic time, which is called T time, for historical purposes, sometimes called longitudinal decoherence, but it's from NMR. That's where the terminology comes from. The whole direction of your magnetization is going to decay. And that means that basically, if you start with your magnetization at time at equal to 0, you wait long enough, and it becomes smaller and smaller and smaller. So this is e to the minus time of T1. However, we need to include another term. And this is a dephasing term. And we can write it down as Sx x plus sy. Why? Right? So this is what's happening in a transverse plane. And it may have a different T2. It may have different relaxation time. What that would mean is that if we started to our precession, as we go along, instead of maintaining this rotation, you kind of acquire more and more uncertainty in this direction. So this is going to be a dephasing. Okay? And I think you talked a little bit about in Raoul's lectures that if you only have kind of radiative types of processes, T2 is going to be 1/2 of T1. However, for spins especially, radiative effects do not play any roles because you really don't have a strong dipole transitions over there. So often T2 is actually shorter than T1. So often, T2 is less than T1. So you're first going to dephase your spin rather than lose your magnetization. And even worse, if you have many different atoms, you can have what is called a T2 star. And this is inhomogeneous one. What inhomogeneous means that it will be different for different atoms. The easiest one to visualize is if you have inhomogeneous magnetic field. So your spins now, depending on their location, they're going to precess slightly differently, and that's going to decohere things as well. So there are actually quite many other effects which can create the decoherence, and they will be more specific for the different systems. For example, especially for the hot atoms, one of the major decoherences in all of the optical sensor is a transit broadening. Because we have the atoms moving through your interaction region, if they're moving, they're leaving at some point. So that means that any time evolution will end when your atom is gone. It's not always huge issue. There are actually a whole bunch of tricks of how hot atoms people figure out how to keep the atoms in. One of them, for example, you add a lot of buffer gas, which doesn't affect the spins too much. So it's like, trying to move in a subway in the morning. You think you're moving, but not really. Another more exotic things is that if you cover your cell walls with some sort of a paraffin coating, which preserves the spins on collisions. And in this case, you can actually have amazingly long decoherence times because even though your atoms left, it will come back to the atoms unperturbed. So there is a way to deal with this. Another one is a collisional broadening. So that usually refers when you have your atoms and they collide with something. I think it's not such a big effect with the cold atoms because you usually don't have a lot of stuff in the system. But you can imagine that colliding with some different species can certainly affect things. Spin exchange collisions. That's actually probably an issue in many cases. It's when the atoms collide, rubidium atoms collide, they're going to exchange their spins, which is not a completely decoherence, but usually not good. And as we discussed, if you have your laser light, which can mess up with things, so we have the power broadening from laser. Physically, what it means is that if you have your spins nicely precessing and collecting information about magnetic field, and now the photons come along and reset it again, which happens when your light is large, okay? And as I said, here what I said is mostly about spins. But in reality, we can think about any kind of coherent superpositions of any two states and use the very similar notations to describe it, okay? All right, any questions? Are we all good? All right, excellent, we're swimming. So now we kind of gave a very brief, so I gave a very brief introduction of what can happen to spins in the magnetic field, or if we think more generally, what's going to happen to coherent superposition of the states if you have some sort of dynamics on your transitions. Now, how are we going to measure it? Okay, I think I can erase this. So I start, we'll see how much I will be able to go through today, but the simplest optical system where we have light interacting with atoms is a two-level system. Okay, so we have two levels and we have electromagnetic field. It's interact with this two level, ground, excited? With these two levels, if level shifts, we will see something with this. We'll start with this one to just briefly go through and establish some methodology, but we'll discover quickly this is not a great idea to use the state for sensing, especially if you use the hot atoms. There's so many things which are not great for that. So in reality, we usually try to use some system where we can create the photonic link between the long-lived states. And for that, we often use a three-level system. So kind of canonical three-level system. This is a lambda system, where we have two states. They can be degenerate when we cannot degenerate. In this case, usually these are the kind of ground states. They can be hyperfine states or Zeeman states. And then we have two optical fields which interacts primarily with these two states. So these are going to be the long-lived. For the lambda system, again, typically these are the spin states we're accessing. This is the optical excited states, so it's a short-lived, but we'll see that you can kind of avoid the, try to avoid the losses associated with it, but also because it's an optical transition, it has a strong interaction, so that's going to be our detection channel. That's what we're going to be looking at. It doesn't mean that we have to use the lambda system. We can also use the ladder system. And in this case, we start with the ground state, we go to the intermediate state, and then we continue going. So we create kind of cascade excitation. In this case, our long-lived states are going to be kind of on the top and on the bottom. And this is going to be our intermediate state. These are long-lived. And usually these transitions serve as our optical detector. You can kind of see that probably that's the scheme we're going to use for Rydberg detection. Okay, just for completeness, there is also among the level schemes a V scheme, but it's rarely used for sensing, especially if you want narrow resonance, just because these are two not long-lived states. So I'm not going to talk about V system at all. All right, but now just to make sure that we are on the same page, let's look in more detail how our light interact with the two-level system. So here again, I'm sorry, I'm going to switch to A and B, just because when we move to the three-level system, it becomes more convenient. And we will assume that our laser has specific frequency and the Rabi frequency omega. We introduce the detuning of the laser from the atomic transition, omega IB minus omega. Again, the Rabi frequency here is going to be the strength of the transition times the amplitude of electric field times 2h bar. And here we need to introduce the actual decays. So we will say that gamma A is going to be excited states lifetime. So that will correspond to kind of T1, which I introduced before. So if we put something up, how long it's going to stay there. And then gamma AB, that is going to be the decoherence. So if we created a dipole moment on this transition, how long is going to stay in phase? Again, if it's purely radiative, that's going to be half of the gamma A, but we can have more parameters for that. Okay? Now, the Hamiltonian for this system, I kind of already gave you, is going to be H delta minus omega star 0. And we go with the Maxwell-Bloch equations. D over dt, density matrix, minus I over H, Hamiltonian of, commutator of our Hamiltonian with density matrix, plus technically lamblading, which takes care of all the decays. But again, you have talked about it on Raoul's lecture. We're just going to throw in decays. Now, for this system, why I have to work with the density matrices is because I need to take into account the decays of the transitions. And really, only the density matrix will allow me to do that. Okay? So in this case, density matrix is simple. We have basically 3 independent elements. So we can say that d rho AA, the population of the excited states, of the excited state, is equal to minus gamma A rho AA. And then that would be the interaction term, minus I omega rho AB plus I omega star rho BA. And the optical coherence, the optical dipole element, d rho AB, that's going to be minus gamma AB minus I delta rho AB minus I omega star rho BB minus rho AA. Okay? You can get this from the Hamiltonian. So these are really the only 2 equations I need, because I will assume that if the atom is not in the upper state, it's in the ground state. So, okay, so in principle, in general, this is the system we're going to solve. In most of the sensing experiments, we will assume that the change in our parameter of interest is slower than the atomic dynamics. So that means that if my magnetic field change, or my electric field change, or my temperature change, my atoms can adapt to this much quicker. So that's called adiabatic following. So that means that I can just solve this equation in steady state and just trace what's going to happen with this. And that makes this equation very, very simple, because basically we can see that gamma A rho AA is connected to minus I omega rho AB plus I omega star rho BA, and that rho AB from this equation is equal to minus I omega star rho BB minus rho AA divided by gamma AB minus I delta. Okay? So the cool things here, we can see that the dipole moment, that's what we're going to drive the optical response, is connected to the population of the excited states in reality. So for many calculations, I can look at the excited state population, and I will know what's going to happen. Okay? Now, I'm not going to go through the algebra. You can do it yourself and try to see if you can beat me writing it down. But you can imagine that this is a pretty straightforward calculations. So we can find that the population of the excited state is equal to omega square divided by 2 omega square plus gamma AB squared plus delta squared. Okay? Kind of makes sense. If no optical field, no population, more optical field, you basically eventually have half of your atoms upstairs. And then, as we discussed, rho BA is equal to minus I omega star gamma AB plus minus I delta 1 minus 2 rho AA. You take this, substitute here, go through the algebra, and you find that rho BA is equal to I sorry, that's I need to take the complex conjugate for rho BA, sorry. So rho BA is going to be I omega gamma AB minus I delta divided by 2 omega square plus gamma AB square plus delta square. Okay? So why I need rho BA at the end? Because this is a component of the optical susceptibility, right? So optical susceptibility from one hand, it is the ratio between the polarization induced in the system divided by the epsilon naught time electric field of your, amplitude of your electromagnetic field, the laser field. But then, of course, since this is the average polarization, essentially what that is the number of atoms we have in the system times the dipole moment for this transition times the rho BA. So this is the average of the polarization divided by epsilon naught electric field. And in our case, if we put all the correct units, we can find that susceptibility as a function of the laser detuning is equal to number of atoms, dipole moment squared, divided by h epsilon naught. So these are the parameters which are given by nature, rho BA divided by Rabi frequency. And if we put the actual value which we have over there, so we will have n DAB squared h epsilon naught I gamma AB minus I delta and 2 omega squared plus gamma AB squared plus delta squared. Okay? Why we, yes?
The line width of the population should be gamma A, right?
Okay, I made a little bit of simplification here. This is the correct answer, but it's actually correct. Only the assumption that gamma AB is gamma A over 2. That just makes it simpler. Yes, so if you assume that, that's the absolutely correct value.
You are only considering radiative.
Yes, so to get this equation, it works only here. It's not going to change things much. It's just make algebra a little more unpleasant if you include separately gamma A and gamma AB.
Also, in your equation, the Rabi frequency is low compared to the decays or something?
At the moment, we have no assumptions yet. So this is the exact solution. The only thing we assume that this is a steady state situation. Yep. Okay. So why we want susceptibility? Because that will tell us the amount of absorption and, in principle, refractive index change. So absorption coefficient And the way I define it is that's going to be the electric field of a laser. As it propagates, is going to be minus alpha z of its initial value. So the absorption coefficient is equal to k over 2, imaginary part of susceptibility. And I wrote it down specifically so we can see easily what this imaginary part is. So we have here number of atoms times k dipole moment square h epsilon naught okay, yes, over 2. Okay, again, these are kind of all the parameters. Now I'm going to put extra gamma AB on this side just to have this ratio to be unitless. So we'll have gamma AB squared divided by 2 omega squared plus gamma AB squared plus delta squared. Okay? As I said, all the parameters over here, they do not depend on our experimental parameters once we chose the transition. Moreover, if you look carefully, if I have no detuning, and if I have a very weak field, all this fraction becomes 1. So that means that this corresponds to the unsaturated resonant absorption. Of an atom. Right? So basically, if you have no detunings and very weak field, the absorption is going to be n times the absorption of the single atom. We're doing it just to make things more easier to write. Okay? And that means that in general, absorption coefficient as a function of detuning is going to be n alpha 0 gamma AB squared divided by delta squared plus gamma AB squared plus 2 omega squared. Okay? So that means that our resonance, if I look at the absorption as a function of detuning, I'm going to have a nice Lorentzian resonance. The maximum absorption I'm going to have is, of course, when delta is equal to 0. So the maximum absorption, it's easy to see, is going to be n alpha 0 gamma AB squared delta square, gamma AB squared plus 2 omega squared. Okay? And the width, let me call it gamma 2 level. That's basically, we see it's half width, half maximum. So we can see that it's essentially square root of gamma AB squared plus 2 omega squared. Okay? And now we can see that actually here, a good example of why having too much laser power may not be a great idea. Because if I start increasing the laser power, what's going to happen to my resonance? So first of all, it's getting broader, and it's getting smaller. Like everything we don't want to do, right? So this is, again, this is a fact. We called it power broadening. And we'll see it's a persistent transition. The more light you put in, the broader your resonance becomes. So we always have to be mindful about this. And here, of course, this is called the reduction of absorption. That's called the optical saturation. And I don't know how many people have heard about it before, or like know about it. It's a pretty common phenomena. Now, my husband, who is also a physicist, has a great explanation of optical saturation. Imagine that you need to cross the river full of hungry crocodiles. So if you have few people crossing, nobody going to cross. So that's what corresponds to the case when you have very few photons and you have many atoms. So somebody will going to absorb the atom, absorb the photon. But now imagine that you have a huge number of people and they just march through the river. Well, some crocodiles, they need time to, to chew on a person. So that means that if you have enough people, somebody will be able to get through. And looks like on average, you're going to have like half people through, many people through. And the same thing happened with atoms. If you have a lot of photons, in many cases, your atom will be on the excited state already and won't be able to absorb. So that's why you have seen less of the absorption. Again, sometimes you may want it, sometimes you may not. But something you will need to keep in mind. I don't know if you experimentalists might be familiar with saturation spectroscopy, absorption spectroscopy. That kind of utilizes this effect that one field saturates and one not. So, okay, where we are. But again, let's go back to the sensors. And you can already see that, having a lot of power is not going to be very good for the sensors. But let's just run through the exercise because it's such a nice, simple system of how we're going to optimize our response. Suppose you have to use a two-level system. So remember in the beginning, we said that the response was the amplitude of our resonance divided by the width. Okay? So that means that the amplitude is going to be, let's say, intensity on the input minus intensity of the output. That's a fair, right? So if you have absorption resonance, that's going to be a fair explanation of how much it is absorbed. And the width, well, this is just the width. Okay. Now, here I will make a little bit of simplification. So depending on the absorption coefficient, if we're absolutely careful, then we have that the output intensity is minus 2 alpha times the length of the system. So it's exponential. However, we'll assume that we are not working with a super dense system, and absorption is not a lot. So we're going to simplify it and say that is I in 1 minus 2 alpha L. I think it's fair. So what it does, it makes this calculation of the amplitude much easier. So that is going to be 2 alpha L divided by, and this is our maximum alpha, of course, if you want amplitude, divided by this two-level, how did I call it? Two levels, yes. Okay, we have expression for that. So our response is going to be basically N. I'm going to keep everything which is not operational parameters of the system, N L alpha naught gamma AB squared times on the top, we're going to have, times the input intensity. Times the input intensity divided by, from the widths and the amplitude, we're going to have gamma AB squared plus 2 omega squared. And we actually have it in the power 3/2. Because one of the powers on the denominator come from here, and the extra 1/2 from here. Now, of course, the intensity here is proportional to the Rabi frequency squared. So there are some coefficients. But you can see that here we have omega square, and here we have gamma square plus 2 omega square in the power 3/2. So if we're going to kind of track how that looks like, what we will find is that if omega is very small, then, of course, our response is going to grow, well, quadratically with omega, right? So that would be a great idea to have more power. However, we're going to reach the maximum, and if our Rabi frequency becomes large enough, now we have omega square over omega cube, so it starts falling down. So we will find ourselves that if we want to use this system, we will basically have optimal parameters to this. And if you do the proper calculations, you will find that this is a Rabi frequency when it's equal to the width of your transition. And in general, you will find that is often the case, where if you have power broadening, you want to be where the width of your resonance, like natural width of your resonance, is about the same as the power broadening. Okay? So that means that if you want to operate it in the sensor, that's the optimal point we want to be. Okay? Any questions so far? All right, good. So I have a few more minutes left. So let me very quickly explain why doing two-level optical system for optical sensors with the hot atoms is not a great idea. And you can suspect that that's because of the Doppler broadening. And you will be correct. So in our previous calculations, we assumed that all the atoms in the system responded in exactly the same way. But if we have a thermal ensemble of atoms, that means that we have to take in mind that we have a Maxwell distribution of atoms. Bless you. Okay? So that means that if we want to know how many atoms move with the velocity, we really only care about the motion along the laser beam. We can calculate that as a total number of atoms divided by the volume of our sample, e to the minus Vz squared over the Doppler velocity squared, Vt, and some normalization. Okay? And just for the records, the thermal velocity is 8 Boltzmann constant temperature divided by pi m. So as we discussed, if the atoms are moving, the detuning will be different depending on their velocity because of the Doppler effect. So in our calculation for the absorption, we will need to replace the detuning, like laser detuning, with this corrected factor. So that means that absorption for the group of atoms with velocity Vz are going to look like alpha naught, gamma AB squared, gamma AB squared, plus delta minus KVZ squared. Here, I assume, I just don't want to write omegas all the time, so this is kind of unsaturated. But it's going to be exactly the same, just with the extra factor. All right. So now, if I'm looking for the total absorption, then, of course, I will need to add the contributions for all the different groups of atoms. And that's going to be the integral over all longitudinal velocities, alpha of delta Vz, number of atoms in this velocity group, dVz. And that's create a fairly long and somewhat unpleasant integral. So alpha naught P KVT. So here we have absorption, gamma AB squared divided by gamma AB squared plus delta minus KVT squared. And in the exponent here, I'm just going to throw in the k vector, just so instead of velocities, we're using the frequencies. So it's minus KVZ squared divided by KVT squared. And we integrate over d KVT, Vz. Okay, so I'm just shifting everything to frequencies. Now, in general, this is a kind of unpleasant integral, as I say. It's called void profile. And it consists of the Lorentzian, which describes the atomic transition. And here we have a Gaussian. It's a convolution, yes, yes. In general, again, numerically, it's, you might need to do it numerically. There is a trick if you really want to. I know sometimes people replace Gaussian with the Lorentzian. It's approximation, but it makes it easier to calculate analytically because you can use the complex numbers to do that. But in our case, we actually kind of don't have to go through all these troubles, is because remember in the very beginning, I gave you the estimates. If our gamma AB, let's say for the optical transition of rubidium, is in the order of 6 megahertz, and our KVT, the kind of Doppler broadening, is on the order of 200 megahertz, they are pretty different, right? So our Gaussian is very broad, and our Lorentzian is very narrow. So it is actually quite OK to replace the Lorentzian with a delta function. And we can just say that in this case, the Doppler broadening, okay, I'll just erase it there. So the absorption profile, Doppler broadening, is going to be n over v alpha naught gamma AB divided by pi kVt e to the minus delta square over kVt squared, okay? So in this case, we expect that the absorption line now is going to be Gaussian. And again, more bad news for us. So first of all, the width now is a Doppler width. So it's much broader than the natural, even the natural line width of the transition. Second bad news is that if you look at kind of unsaturated absorption, now you have a factor of natural line widths over the Doppler line widths. That's another factor 100 for you. So as I said, it's not a great idea to use the optical system to do the sensors. It's not bad. Sometimes if you want to measure very strong fields, it might be just what you need. You don't want super sensitivity. But in general, interaction with a strong laser field broadens the transition, and it saturates the resonance. And if the atoms are moving, they're doing even more of that. So I guess next time, we'll talk about how we can go to the 3-level system to avoid some of the issues with the 2-level system. All right? Thank you, guys.
Qual é a unidade